Hi there, my name is Simon and I'm the CEO and co-founder of Fast Track. I'm excited to be here today to talk about artificial intelligence and machine learning and tell you more about how it all actually works. For many of us, machine learning is like a black box. We know it's something cool with tremendous power and it will have a huge impact on our lives, our organizations and our customers. I started studying AI and machine learning a few years ago, and my philosophy was that if I'm going to be successful in this space, I need to understand how it works. And we all learn in different ways, right? I like to be able to visualize things and interact with it in my mind. I want to be able to step into the future and see how all of the pieces fit together. I have a really hard time letting go until I get that penny drop moment and everything kind of just makes sense to me, right? I started my own journey with Google and YouTube. I watched an endless number of videos and read a lot of articles on this topic. And a good place to start is probably to explain what the difference is between AI and machine learning and what it actually means, right? And without being politically correct and with the risk of pissing off some data scientists here, for us common people and for myself, AI and machine learning means the same thing. You can say building an AI model to solve a problem as much as you can say building a machine learning model to solve a problem. Personally, I tend to use artificial intelligence when I speak in terms of the overall science, like I would use words like mathematics or biology. The science of which I'm referring to is to mirror human-like behavior and build intelligent programs that can help solve problems. Machine learning for me is more like a practical term, like developing the actual software. Machine learning can be applied in different ways, depending on the problems that you're trying to solve. To cover the basics, I would like to tell you about two different types of learnings. The first one is unsupervised learning. Unsupervised learning is a technique that you can use when you have untagged data. Okay, that might not make too much sense, but take for instance that you have a comprehensive amount of behavioral data about your players and you would like to identify different behavioral profiles. You can then use unsupervised learning as a method to find similarities in your data and split them into different groups. This is most commonly referred to as clustering. The second one, which is the one I want to focus on today, is supervised learning. And supervised learning is when we study what we know. So by providing both the answer and meaningful data that can help determine that answer, we can use computing power to find patterns in that data. And if successful, the machine will determine the correct answer simply by looking at the data. This should make a lot of sense since pretty much everything that we have learned in school has been taught to us this way. There was a time when you and I did not know what an apple was. But by showing us apples, letting us taste the apple and ultimately telling us, right, that this is an apple, over time we have figured out and programmed our mind to know when we're tasting or seeing an apple. This is supervised learning. I encourage you to check more clips about this individually, but in this session I will focus on supervised learning. I think the basic theory of the machine learning is quite easy to comprehend. We provide data and then this is processed through a mathematical algorithm and then outputs a result on the back of it. It makes sense, right? But what left me a bit more frustrated was how little they shared about the specifics. It was not clear how this data actually needed to look like and when entering into the model, how it needed to be formatted. And the same going for the output. How can I make use of it? This made it difficult for me to understand the end-to-end logistics. For me, the specifics are very important. I want to be able to talk in practical terms. I want to be able to see if the data I have and the systems I have will be compatible with what I'm building. And if there is one thing that you should take away from this session today, it is that the key to a successful machine learning strategy lies in the process. Now, I want to tell you how it works. Let's build a supervised model together. To do this, we're going to need a problem. And a very relevant and difficult problem we're dealing with currently is our ability to prevent harmful play. This is an excellent candidate to work with and a great example where machine learning can be very powerful. Let's say that we would like to build the following model. I want to process player data on a regular basis and determine whether the player is likely to develop a harmful behavior. In a passing conversation, what I just told you might make perfect sense and something we should immediately invest in. However, it's not time to push all in just yet. If you look at this a bit more closely, you will see that there is a couple of different terms that needs to be better defined. Machines are not smart enough to figure out stuff on its own. At least not these things. I want to process player data on a regular basis and determine whether the player is likely to develop a harmful behavior. What is player data? What does it mean to be doing this on a regular basis? At what time do we actually want to predict this? And what determines whether the player is likely to develop harmful behavior? We need to understand all of these in detail. Machines do not have room for interpretation. We have to be explicit. But don't worry, there is a way to fix that as well, right? So the trick is to scope in reversed order. Work your way back from the objective. In order to define what player data we will use and what we mean by doing predictions on a regular basis, we need to start with the actual problem. What determines whether the player is likely to develop harmful behavior? If we can't figure that out, nothing else matters. And in this particular case, depending how we look at it, I can see a number of different options available to us. For example, we might say that we have a team member, Christina, who is working with us, and she's the only person that is skilled enough in order to be able to determine whether a player is likely to develop a harmful behavior. As a matter of fact, it's perfectly fine to rely on Christina in this particular case if you're convinced that she's right. In that case, we would ask Christina to provide us with a list who she deems are showing harmful behavior and another list which are players that are showing responsible behavior. This would be enough. We need to know and show both positive and negative observations in this process. Or we might say no, the way to define this is to look at who contacted us and who has been playing more than they can handle. This is also fine. Instead of relying on Christina in this case, we can rely on an extract of players from our customer support platform who has contacted us in this concern. Whether we rely on Christina or in this case the live chat platform to get a list of players doesn't really matter. The most important is that we have observations which we can rely on. We have to be able to guarantee that whatever observations we use to train the model are indeed correct. With other words, when building a supervised model, we must, in one way or another, supply the model with a list of observations to learn from. This list must contain both positive and negative observations, or in other words, in this particular case, both players that show harmful behavior and players that play responsibly. And the more observations we can provide, the better our chances are to build a reliable machine learning model. Now, let's pause for a second and touch on some machine learning lingo. What we're trying to define right now, whether the player is likely to develop a harmful behavior, is what data scientists would refer to a target feature, or a target. Whether this is true or false will be referred to as target classes. And this type of machine learning model is called a classification model. Let's say, hypothetically, that we stand behind Christina on this one, and I can guarantee you this step is the hardest of them all. You will not always have people like Christina around you to help you. At Fast Track, for instance, we can spend months trying to agree on clear definitions. Anyway, moving on, regular basis. I want to process player data on a regular basis and determine whether the player is likely to develop a harmful behavior. Let's chat what it means to do this on a regular basis. Maybe to start with, actually, why is this even important? Isn't it clear? Our intention is to build a model that can run at multiple points in time, it's on a regular basis. Well, no one is arguing on that point. We just need to recognize that there will be a point in time when we make the first prediction. And we need to know when this will be in order to see what data is available to us at this point in time. Take, for instance, that we develop a model, we decide to bring tons of interesting data into it, like how many deposits the person has made, whether the player plays high or volatile games, or if he's having an erratic betting behavior. But then it turns out you actually wanted to predict at the point of registration. The model will not be trained on this data, and it will be trained on data that is not accessible at this time. Meaning that you're taking the model out of context and asking it to solve a problem which it's not trained for. it's important to include this in the problem description or in the scoping of this model. Luckily for us, Christina is an expert in this field, and she just gave me a call and told me that it makes perfect sense to trigger a prediction after each deposit, starting from the second deposit onwards. Great. Then we can finally move on and discuss one of the most exciting aspects of data science. We call it feature engineering. I want to process player data on a regular basis and determine whether the player is likely to develop harmful behavior. We are now ready to discuss player data. Data that enters into a model is referred to as features. Features, variables, data points, columns, attributes, fields, properties, parameters. Well, there is probably another 10 words which I can't even think of right now that can be used to describe the same thing. Bottom line is that when we talk about features, we talk about data. And not any data, not raw data, but meaningful data. The engineering part of feature engineering is the idea of making raw data meaningful to us. You tell bits of stories through your data. So I want to process player data on a regular basis and determine whether the player is likely to develop a harmful behavior. What player data is both available and meaningful to us in this case? Take the bet and payment history of a player. In raw format, row by row, it tells us almost nothing. This data is available, but it's not meaningful. To make this into something meaningful, we need to look at the data collectively. Out of this, we can come up with relevant features in relation to our problem. For example, did the player change his betting behavior? How many deposits did the player make in total? How many withdrawals were reversed? Are there failed deposits reattempted with a lower amount? How many failed deposits were succeeded by a deposit using a different method? How many times did the player go from high balance, ran out of money, and immediately went to redeposit? How many payment methods have been used? Has the player used third-party cards, not in his own name? All of this is meaningful and is relevant when trying to identify whether a player is developing a harmful behavior. All of this data should also be available to us, since we said we will run the predictions on the second deposit onwards, and base it on the raw transaction history, of course. So, we have now defined what player data we need. At this stage, the scope of the model has been defined. I want to process player data on a regular basis and determine whether the player is likely to develop a harmful behavior. We know what we need, we know when we need it, and we know why we need it. Creativity is everything when it comes to feature engineering, and this is a huge portion of the responsibilities of a data scientist. It is therefore key that he has access to a lot of data, of course, but also has a good understanding of how your business actually works. Whatever data we use to train the model will also be required when we make predictions. If you're too creative and you don't have access to this data when you want to get a prediction, even the greatest and smartest model ever will be completely useless. This is important to know early in the process. Finally, now when we have the data we need to put this into a spreadsheet and feed it into an algorithm. As I mentioned in the very beginning, I was struggling to understand the format we need to work with when feeding data into an algorithm. The format is actually very common. In most cases, we use a spreadsheet and we save it as a CSV. In simple terms, what will happen in this case is that we will ask Christina to send us a spreadsheet with a list of players, one per row, and in a separate column, include the observations whether the player is showing harmful behavior and mark those as a 1, and players showing responsibly marked as a 0. We will then add these features to the spreadsheet, one additional column per meaningful feature. Spreadsheets we use every day, and it's good to know that the data scientists are using the same format. Almost every algorithm trains with observation in this format. The next crucial step in the process, once you have the final spreadsheet, is to divide it into 2 parts, and I will tell you why. In the first spreadsheet, you will include the training set. In the second spreadsheet, you will include the validation set. Whilst training the model, we will only expose the data in the first spreadsheet, the training set. And when validating the model, after it's been trained, we will make predictions on the observations in the second spreadsheet, the validation set, to see how good the model really is. The actual splitting sequence is simple. We just take a random sample, say between 10 and 20% of the rows, and put these in the validation set. And once you have it, you need to stick to it. The process of developing a machine learning model will go back and forth, okay? We might train the first model and we will find out that it's not accurate at all. What we believe to be meaningful features are in fact not meaningful at all. Then we need to go and find new meaningful data and create a new version of this model that we can use with different features. When doing these changes, it's crucial that the validation set remains the same, so that you're testing the model on the same data set, comparing apples to apples. The last final piece is the algorithm. If anything can be considered a black box when it comes to machine learning and AI, the algorithm would be the one. In reality, this couldn't be further away from the truth though. There are tons of algorithms available, and in most cases they are published in articles and they provide complete transparency on how they work. But yes, in order to understand and validate an algorithm, you will require advanced mathematical knowledge. So it's safe to rely on algorithms that has been validated by the community. That's what we do. In supervised learning, common algorithms include decision tree, random forest, KNN, logistic regression, and neural networks. What you need to know at this stage is that different algorithms are designed to tackle different problems. Something very useful to know as well is that the format that is feeded into these algorithms are fairly similar, and it's not one big job to try another one. And putting this all together will require a bit of coding, of course, and we don't have that right now, but we do have a model, at least hypothetically. I hope you found this useful and that it made you curious to learn a bit more about machine learning and AI. There are 3 things I would like you to take away from this session today. Number 1, machine learning models are specific and logical. They are not living their own lives and solving problems on their own without human interaction. Even the most complex systems are solved by solving one small problem at a time. Number 2, build a capacity internally. As you have seen today, it's not that hard to get your head around this. And I strongly encourage all organizations to build an internal capacity to work with this. You should be in control of your data and your decision making. And number 3, involve your entire organization. Everyone can contribute to this process. All knowledge is key. Do not ring-fence AI initiatives to specific teams. And please watch this space. Follow Fast Track and come and watch our next appearance at iGaming Next in November. Just like we have redefined the meaning of CRM for the industry, we will be announcing a brand new revolutionary product which will fundamentally change this industry and how we work with machine learning. With this, I would like to thank you all for listening in today and wish you a wonderful day. Thank you very much.